What's up? This is Mr. Rodriguez, and in this video, we are going to be going over the solutions to the problem set that's meant to follow my lecture on rotational kinematics. I suggest you download the blank problem set below or in the description of my rotational kinematics lecture video. I also suggest that you watch the lecture video for rotational kinematics before attempting this problem set. Feel free to attempt the problem set on your own, but in physics, some things are better explained through examples. There are going to be some topics that are going to be elaborated on in this video as we solve some of the problems that may not be in the lecture. So also feel free to continue your studying as you watch me talk through the solutions to these problems. Good luck studying. I hope you enjoy. For the first problem, we have a graph that plots angular speed in radians per second versus time in seconds. And the question says, an object rotates with an angular speed that varies with time as shown in the graph. How can the graph be used to determine the magnitude of the angular acceleration of the object? All right, well, first off, let's remember what angular acceleration is defined as. Angular acceleration is going to be defined as the change in our angular velocity over change in time. Now, that said, if we have angular velocity on the y-axis and time on the x-axis, then acceleration is just going to be defined as our y-axis over our x-axis, which is the same thing as slope. So if you notice B here, it says determine the slope of the line from 0 to 2 seconds, so from here to here. Determine the slope of the line from 0 to 2 seconds because the slope represents change in angular velocity over change in time, and that is the definition of angular acceleration based off of our lecture. So we're going to go ahead and circle B for this problem. For some of the other answer choices, like C, it says determine the area bounded by the line. The area underneath an angular versus time graph, that's going to actually be the change in angular position. That's going to give you your actual change in angular position over this time period. Let me see. D says the angular acceleration cannot be determined without knowing the rotational inertia of the object. The definition of angular acceleration doesn't actually take into account angular inertia. And for A, it says subtract the greatest value of angular speed from the smallest value of angular speed. That's just going to give you the change in angular speed. It's not going to give you the angular acceleration. We need to divide it by the change in time as well. All right, so the answer is B here. Here for problem 2, we have kind of a longer problem. It's actually easier, but there's more words, which is something that kind of throws a lot of people off. Two small objects of mass m0, so both of the objects have the same mass, are on a rotating platform of radius r and rotational inertia I. It's rotating about the center, and they compose a single system. Students use the system to conduct 2 experiments. The objects are assumed to be point masses, so they don't take up any volume. Each object of mass m0 is placed a distance r1 away from the center of the platform such that both masses are on opposite sides of the platform. You can see that from the image here in figure 1. A constant tangential force is applied to the edge of the platform for time delta t0, as shown in figure 1. The system was initially at rest. So just pausing there, if we have a constant force being applied to anything, whether we're talking about linear motion or rotational motion, that means it must be accelerating. If we have a tangential force applied here, then that means it will be accelerating. It will be experiencing angular acceleration. All right. Now, for experiment 2, each object of mass naught is placed some distance r2 away from the center of the platform, such that both masses are on opposite sides of the platform. R2 is less than R1, and a constant tangential force is applied to the edge of the platform for a time delta t, as shown in figure 2. So experiment 2 is a little bit different from experiment 1, but both situations we have a constant tangential force being applied so that the disk should be experiencing angular acceleration. But the question doesn't even care about experiment 2. It says, which of the following graphs represents the angular displacement of the system as a function of time for the system in experiment 1? So for the system in experiment 1, we're plotting angular displacement versus time in every single one of these. Now the question is, how is angular displacement going to be changing with respect to time? All right, and we know that the disk is going to be accelerating. So that means angular displacement is going to be increasing at an increasing rate. So what that means is, first off, we're going to have some kind of a positive graph here. So I'm going to basically take off D. D is no good. because we know that angular displacement is going to be increasing. And we also know that it's going to be increasing at an increasing rate. So B suggests that it's going to be increasing at a decreasing rate. Notice how it starts off increasing very quickly and then it starts slowing down on its increase. That's not what we want. A suggests that it's increasing at a constant rate. So that means we would have constant acceleration, that we don't have any acceleration, that we have constant velocity. That said, C is the only one that suggests that we're going to be increasing at an increasing rate, and that suggests that we have angular acceleration. So here we have a graph of angular velocity versus time. All right, so you just have to keep in mind that this omega sign is angular velocity, since the graphs aren't properly labeled. A graph of the angular velocity omega as a function of time t is shown for an object that rotates about an axis. All right, so there are 3 different time intervals, 1, 2, and 3. Which of the following correctly compares the angular displacement delta theta of the object during each time interval? All right, so here's what you need to remember here. When you have an angular velocity or any velocity versus time graph, then the area underneath the curve represents angular displacement. And that's actually used to derive one of the kinematic equations. All right, so something like displacement, in this case, let me use my pen, change in displacement would be equal to 1/2 v final times t. That said, what this equation basically represents is the fact that the area underneath a curve represents the change in displacement. All right, that said, we have 3 different sections here. So I'm going to partition this graph into the 3 different sections. And I basically have 3 simple shapes here. I have 2 triangles that are identical to each other, and then I have a square. It looks kind of like a square that's about the same width as the triangle, so I know that it must have more area as the triangles. That said, that tells me that during the time interval 2, we're going to have the greatest change in displacement. All right, and then so 1 and 3, assuming they are the same width, okay, then we'll have equal changes in displacement there, since the area underneath this curve will be the same as the area underneath this part of the curve. So it looks like for section 2, we'll have the greatest, and then 1 and 3 should be the same. The only answer choice that suggests that is answer choice B, where it says delta theta 2 is greater than delta theta 1, which is equal to delta theta 3. That's exactly what we just suggested up top. So answer choice B is what we're going to run with. So for this problem, we have an axle and a mass hanging from a pulley. So the question says, an axle passes through a pulley. Each end of the axle has a string that is tied to a support. A third string is looped many times around the edge of the pulley, and the free end attached to a block of mass MB. So that's what we see here. The free end is attached to this block of mass MB. It is currently being held at rest, but when the block is released, the block will fall downward. It's going to fall downward due to the force of gravity, by the way. So keep that in mind, because that's important for the question. Consider clockwise to be the positive direction of rotation. Frictional effects of the axle are negligible. That's good to know. And the string wrapped around the disc never fully unwinds. So because friction in the axle is negligible, then the force due to gravity is going to represent a constant force that's causing this mass to accelerate downward. Okay, it's going to be a constant acceleration downward because gravity has constant acceleration, but that means that the velocity of the block is going to change with constant acceleration. So over here on our graphs, if they're all angular velocity versus time or velocity versus time, then we can expect velocity to increase at a constant rate if acceleration is constant. And we know conceptually that acceleration is constant because acceleration due to gravity is constant. So the only one that shows constant increasing is actually answer choice B. Sorry if I jumped the gun there. The question is, which of the following graphs, if any, show the angular velocity of the pulley as a function of time t after the block is released? And we just described why that's actually B. Answer choice A shows that the angular velocity doesn't change, but is some constant value. All right. C says that the velocity is going to be increasing at an increasing rate. That would only be true if our acceleration is increasing over time. That's not going to be the case. And then D shows that the angular velocity is going to start at some value and then go to 0. So we already were told that it started from rest. So we need one that's going to start from rest. We need a graph that shows that the angular velocity is going to start at 0 and that it's going to increase consistently. So the only one here is B. Here we have a graph that plots angular position versus time. And it looks like on the graph we're starting from 0 and our position is changing with respect to time in a constant manner. So that means we have some velocity, but we have no acceleration. So that's what you should be thinking as soon as you see this kind of a graph. And the question says a disk of radius of 50 centimeters rotates about a center axle. The angular position as a function of time for a point on the edge of the disk is shown. Which two of the following quantities of the point on the edge of the disk can be correctly mathematically determined from the graph using the method described? So there's these answer choices here are saying that you can find some information based off of what's in the graph. It wants us to pick two answers. So let's look at A first. A says that the angular velocity, you can find the angular velocity because this quantity can be determined by calculating the slope of the graph. All right, so that's suggesting that angular velocity is defined as change in position over change in time. And that is indeed true, and that would be the slope of this graph because it's position versus time. So yeah, A is definitely true. Let's look at B. The translational speed, because velocity, that's linear velocity, is equal to the radius times the angular velocity. Well, that is how you find translational speed, and we do have the radius, it's given here, and we do know the angular velocity if we use the slope of the graph. So I would say, yeah, we can actually find the translational speed here, or the linear velocity. All right. So let's see C, the angular acceleration, because this quantity can be determined by calculating the area bound by the curve and the horizontal axis from 0 to 5. Now what's interesting is that we do know the angular acceleration. It's 0. This graph having a constant rate of change suggests that acceleration is 0 because that means that velocity is staying the same throughout this 5-second time period. But it's not true that the area underneath this curve is that acceleration. The area underneath this line is clearly not 0. So this statement, while we can find the angular acceleration, not in the manner that it suggests. So we're definitely not gonna circle in C. I mean, we've already picked 2, so that means C and D are probably not right, but let's review them just to make sure we know what they're saying. D says the translation acceleration because A is equal to V squared over R. Interesting. So no. First off, because V squared over R is centripetal acceleration. All right, so that's not the same thing as translational acceleration, and it's just wrong. Alrighty, so that's that for this one. For this one, we have a graph that plots angular velocity over time, and it shows us that graph from 0 to 4 seconds. The question says, the graph shows the angular velocity as a function of time for a point on a rotating disk. The magnitude of the angular acceleration at the disk at t equals 2 is most nearly what? Okay, so one thing when I look at this graph is that I know that from the time 0 to 4, the magnitude of angular acceleration should be the same because velocity versus time gives us angular acceleration when we take the slope of that graph, okay? Because angular acceleration is just defined as change in velocity, change in angular velocity over change in time. So at the slope at any point on this graph is going to tell me what the angular acceleration is at that time. The interesting thing is that this is a linear graph. So that means that the acceleration is the same throughout the entire graph. So on a straight line, the slope doesn't change from point to point. That said, all I need to do is find the slope of this line, and I should have the acceleration at any point from 0 to 4. So that said, I'm just going to go ahead and I'm just going to do the slope formula here. So I'm going to say 4 minus 0, or I'm sorry, 8 minus 2. We're taking the angular velocity up top. 8 minus 2. And I chose 8 minus 2 because those are my top and bottom point. And I'm going to put that over the times that coincide with them. 4 minus 0. All right. So that's going to give me 6 over 4, which should simplify to about 1.5. And so let's think about what units we're dealing with here. You should generally carry your units with you. On top, we had radians per second. And on bottom, we had seconds. So then that's just going to, of course, end us with some acceleration, radians per second squared. Radians per second squared. And that is, of course, one of our answer choices. In this problem, we have an object that revolves around a central axis of rotation. So think of it like it's just somewhere on a disk that's rotating. The motion of the object is described by the following equation. It's omega squared here. Omega squared, this is omega final, is equal to 10 radians per second squared. So this is also a value for angular velocity, minus 4, and then the units of acceleration, radians per second squared, times some theta. Okay, so then it says, which two of the following graphs correctly show the angular motion of the object? Select two answers. Okay, the trick here is going to be able to recognize that this is in the form of one of the constant acceleration kinematic equations. And the one that it looks like, I'll go ahead and write it down. So you should have these memorized, or you should have them on a formula sheet so that you could be like, okay, well, which equation does this look like? It looks like this one, where we're taking the square of our final angular velocity and setting it equal to the square of our initial angular velocity, which is what you'll see right here. All right. And then we're going to add 2 times the acceleration, or the angular acceleration, times some change in theta. Okay. So if I go ahead and match everything up here, so this theta is just that theta, okay? This 2 alpha goes here, all right? This 2 alpha goes here. Then what I'm going to notice is that if I just take that plus 2 alpha, here, let me get my pen, that plus 2 alpha, that should be equal to this negative 4 that I have in radians per second squared. So what that tells me is that my alpha, if I divide by 2 here, my alpha, my angular acceleration should be negative 2. All right, so that's a lot of information that we've just gleaned from this graph. And now let's see if that's enough information to tell us which one of the graphs, which of these answer choices that are graphs is true. All right, so for A, it says that we have constant angular acceleration at negative 4, but we just found out that our angular acceleration is negative 2. So yeah, our angular acceleration is constant, but it's not negative 4, so I'm going to cross that one out. For B, it looks like we have it's angular. This one's just angular velocity versus time, but it does look like it has a constant negative acceleration. Let's check really quickly to see if it's at negative 2. So if I do 10 minus 2 over, let me see. Yeah, actually that should be 2 minus 10 over 4 minus 0 over 4. That should give me negative 8 over 4, which is going to be negative 2. All right, so based off of finding the slope here, this is a constant negative acceleration of negative 2. So this graph could work. This graph could work. For C, we do have a decreasing rate of change in position. So this graph, it has a higher slope here than it does here. Then that means velocity is decreasing. That said, that does suggest we have negative acceleration, but I think in order to figure out if the negative acceleration is correct, we're going to need one of the constant acceleration kinematic equations, one that has final position and initial position. And I believe the one that we want to work with here, and I'll do it in blue over here, is theta final is equal to theta initial plus, let me see, initial angular velocity times time plus 1/2 angular acceleration times time squared. All right. So from here, let's see. Our initial angular velocity should have been 10 radians per second. That's given to us in the equation. So I'm going to go ahead and plug that in here. And I'm going to plug in everything else that I need. But before that, let's go ahead and do the algebra intelligently. Let's go ahead and solve for this first. So then we're going to have change in theta, and I get change in theta by moving this over, minus initial velocity times time, all right? All of this times 2 divided by time squared. All right, so that's a couple of steps of algebra that I did where I just basically multiplied both sides by 2 here so I got that here, and then I divided by the time squared over here to isolate alpha. This is all equal to alpha. Now I'm going to plug in a few things. I know that my change in position over the time was initial position of 0, a final position of almost 25. I'm going to say 24. All right, so we have 2 times 24 minus, we have 10 radians per second as our initial angular velocity, but the time frame is 4 seconds, so I'm going to go ahead and put 40 here. And I'm going to divide that by the 4 squared, so that's 16. And I said 4 squared because our total time here was 4. And all of that should be equal to -2. All right, so, or at least it should be very close since we made a couple of approximations. So I'm going to do 24 minus 40 times 2, and I'm going to divide that by 16. And sure enough, we get an acceleration, an angular acceleration of -2. So that means C is actually correct for us. C is correct for us, and since we only need to pick 2, I'm going to go ahead and pause there, because for angular velocity, I can already tell you that this one, first off, it's going to be very rare that you see angular velocity plotted with angular position. We don't necessarily have the information there to find the acceleration. In this question, we have a uniform disk that's spinning with some initial angular velocity w sub d, and then we have a graph showing that angular velocity as it decelerates with time. The question says, a uniform disk spins about an axis that passes through the center of a disk and is perpendicular to the plane of the disk. The disk has an initial angular velocity omega d here, okay, and uniformly accelerates to rest over time. So it's decelerating with constant deceleration. The angular velocity of the disk as a function of time is shown in the graph, okay? So a student must determine the angular displacement of a point on the edge of the disk from time is equal to 0 to the instant in time the disk comes to rest. But if the point's initial velocity was changed to 2 omega sub d, so twice the initial angular velocity, but its angular acceleration is the same, okay? How can the graph in figure 2 be changed before the student can determine the angular displacement? Okay, so the answer choices are like long explanations. So I want to just talk about the graph for a second, because it says, how would we change the figure? Let's see, how can the graph be changed? Yeah, so how would we change this figure if the initial velocity was twice as big, but the acceleration was the same? So here's the thing. You have to remember that the slope of an angular velocity versus time graph is the angular acceleration. So that means if the acceleration is staying the same, then whatever the graph is going to look like after we change it, it's going to be a parallel line to the line that's already on the screen. That said, the initial angular velocity on the graph now is right here. So if we were going to double that, then it's annoying that they didn't draw the graph high enough, but it looks like about right here, and I'll do this in red, we would just have to make the y-intercept here, and then we'd end up having a graph that was parallel to the graph that's already on the screen. And the only reason I said here is because I'm estimating that this is twice as high as the initial y-intercept. And the reason why I'm wanting to make that twice as high is because this y-axis is our angular velocity, and this x-axis is time. So on the y-axis, we have time 0. So whatever point we have on the y-axis is going to be our initial angular velocity. The question just says, how would the graph change if we doubled the angular velocity? Well, it would look exactly like what we have here in red. It would just have double the y-intercept, and it would be a line that's parallel to the graph that's already on the screen, because acceleration is still the same and it's still constant. So now that we know that, let's go ahead and see if which one of the answer choices lines up with what we already know to be true. A says, recreate the graph with a vertical intercept that is twice the value of the intercept shown in the figure. Okay, good. Because the angular velocity is increased from omega to 2 omega. The horizontal intercept should be the same in both graphs. Okay, that's not going to be true, because clearly this graph is going to touch somewhere else on this horizontal intercept than this graph is, okay? So let's move on to B. Recreate the graph with a vertical intercept that is twice the value of the intercept shown in the figure 2, because the angular velocity increases from omega to 2 omega. That's true. The slope of the line should be the same in both graphs. That's true, because the angular acceleration is the same in both graphs. Okay, I mean, that's all absolutely right. I'm going to go ahead and circle B for now, but let's go ahead and keep reading. C says, recreate the graph with the same vertical intercept on both graphs. Okay, already no. We don't want it to have the same vertical intercept on both graphs, because we know that they have two different initial angular velocities. So C's out. Of course, A was out already too. And then for D, it says, recreate the graph with the same vertical intercept in both graphs. Okay, no, again, we don't want the same vertical intercept on both graphs. We need to have the vertical intercept twice as high. So the only answer we have left here is B. So in this problem, we have two identical wheels, wheel 1 and wheel 2, and they're both initially at rest before they begin to rotate with constant angular accelerations, A. After rotating through the same angular displacement, the angular velocity of wheel 1 is omega 1, and the angular velocity of wheel 2 is omega 2, which is equal to 3 times omega 1. So clearly, wheel 2 was accelerating with a greater angular acceleration. All right, so that said, how does the angular acceleration of wheel 2 compare to the angular acceleration of wheel 1? All right, this is actually a pretty fun one to investigate, but in order to truly investigate it, we're going to need a kinematic relationship that takes into account constant acceleration and uses the terms displacement, acceleration, and angular velocity. Okay, so the one that comes to mind here is, let me see, omega final squared is equal to omega initial squared plus 2 times angular acceleration times our change in position, so our change in theta. All right, so this has all of the things that we're discussing in this question, and let's kind of evaluate the acceleration for the first one. It's all going to be symbolic, of course. We don't have real values here, but I'm just going to go ahead and solve for a1. Okay, so that means that I'm suggesting that we have an initial velocity of 0, and that our final velocity is just going to be omega 1. So then that means we have omega 1 squared is equal to 2 times our angular acceleration 1 times delta theta. And I'm going to solve for angular acceleration 1. So that means I'm going to basically divide both sides by 2 delta theta. So that means I'm left with angular acceleration 1 is equal to the square of angular velocity 1 over 2 delta theta. All right, that's great. Now, let's go ahead and set up the same equation and solve for angular acceleration 2. All right, so that means that I'm going to be dealing with angular acceleration 2 squared, and then angular velocity 2 squared. The initial angular velocity for both was 0, so that term's not going to come into place here at all. And then so it's going to be plus 2 times angular acceleration 2 delta theta. All right. Now, the only difference here is that we can rewrite omega 2 as 3 omega 1, and that's going to allow us to find out what how the accelerations compare. All right. So that said, I'm going to say that let's go ahead and solve for a2 first, and then we'll plug in the 3 omega 1 for omega 2. So it's going to look exactly the same as this top one, but it's going to be omega 2 squared over 2 delta theta is equal to angular acceleration 2. All right, so hopefully you can see that this is the same thing here. But now, instead of omega 2 for angular acceleration 2, I'm going to actually write that as the quantity 3 times omega 1 squared over 2 delta theta. And if I go ahead and distribute this exponent, then what I'm going to be left with is 9 omega 1 squared over 2 delta theta. And how does that compare? Let's like literally put them next to each other. How does that compare? Oops, I don't want to move the whole picture. How does that compare to what we have for angular acceleration 1? All right, if we compare that to angular acceleration 2, it looks like there's just a factor of 9 difference there. So then we can say that angular acceleration 2, is just 9 times angular acceleration 1. And so answer choice that actually coincides with that is answer choice D.